Ratchet mechanisms allow free movement in one direction and prevent movement in the other. But what about a mechanism that can ratchet in either direction? Well, the obvious example here is the ratcheting socket driver that requires flipping a switch to change the direction. But in this video, I design and build a new device that can ratchet in either direction without the selection switch. It will make more sense later in the video, I promise. Let's start with the heart of the mechanism, which is the ratchet wheel. To simplify the mechanism, I wanted to make it with a single ratchet wheel as opposed to stacking two traditional ratchet wheels with their teeth reversed. And this turned out to be a real challenge. Let me explain. This is a traditional ratchet wheel I made for the Patreon watch project, and you can see that the teeth are asymmetrical. For a mechanism to ratchet in either direction with a single ratchet wheel, the traditional shark fin-like tooth profile won't work because it's not symmetrical. Rather than inventing a new gear profile, I decided to make a pin gear which can be made using traditional tools and techniques. In this case, I used the pantograph with a 3D printed template which allows me to machine the holes, spokes and cut it from the plate all in one machining operation. Once the part is finished on the pantograph, it needs deburring and cleaning up with files and emery paper. One side of this component needs a chamfer, and the reason for this will become obvious later. I do this on the watchmaker's lathe using the 6-jaw chuck. I decided to machine the wheel hub from a separate part and then bond them together. The hub is bored to 5 microns over the axle diameter and then parted off. It's important that the faces that contact the wheel are accurately aligned with the bore, so I make sure to machine these bits together without moving the material in the chuck. The reverse face doesn't matter, so I just clean it up in the 3-jaw chuck. Retaining compound can form a really good bond when used correctly. In this case I'm using Loctite 638 because I had it on hand, although normally I would opt for the lower viscosity 603 for well-fitting parts like these. Because these adhesives are anaerobic, it's best to apply in excess to make sure there is no air left in the joint gap. The pinholes in the wheel are machined undersized on the pantograph and then opened out slightly with a reamer. I open the top portion of the hole to help locate the pin and leave the bottom portion undersized so the pins will be a tight press fit. I'm aiming for the tightest fit possible without distorting the wheel. I press fit the pins using an arbor press, and I also apply a drop of adhesive for added security. I made a fitting for the arbor press to help align the pins vertical. The main axle is fitted to the wheel and cross-drilled to provide an attachment point for a cable. It's this cable that will be actuated. This next component is the base plate, which locates the positions of the key components. I made this using a similar technique to the wheel, so this is my opportunity to tell you a little bit more about where the idea came from. An old colleague from my time at the University of Southampton, Dr. Charlie Burson-Thomas, has this vision to really understand the nuances of joint biomechanics, with the goal of using these learnings to inform treatment strategies for conditions such as osteoarthritis. The human hand is a good place to begin because we use our hands for almost everything we do, from tying shoelaces to typing on the computer. And yet there is currently no good treatment strategy for osteoarthritis in our fingers. With help from the FortisNet research network tied with the Institute for Life Sciences, we could take the first steps in making Charlie's vision a reality. The truth is, a project of this scale is a lifetime pursuit, but you've got to start somewhere, right? So let's first start with the simplest aspect, which are the kinematics. If we move our tendons by, say, 1mm, how far can we expect our fingertip to move? Our job as Cronova was to build a device that could interface with tendons in a cadaveric hand and actuate them by a known amount in either direction. Although we don't know exactly what our tendon forces are, which will form the basis of a future experiment, they could potentially be quite large, and so our actuator has to be able to cope with this. On top of this, the actuator needs to work in an X-ray CT scanner for future experiments, and ideally be able to move the tendon quickly for viscoelastic measurements. Of course, there's more than one way to do this, but my proposed dual-directional ratchet mechanism offers a good compromise between all of these requirements. So with that in mind, here's the idea. The pinwheel forms the basis of the mechanism, which is locked with the two long arms that are situated on either side of the wheel. The mechanism is actuated with a high-performance wing servo motor, and the various cams are carefully designed to control the movements of the push rods attached to the servo horn and the locking arms. 3 spacers, which you've just seen me machine, locate the rear bearing support, which interfaces with a simple rotational damper I designed to prevent the mechanism's skipping teeth when ratcheting with the tendon tension under high loads. To make the rear bearing support, I used the pantograph once again, and because I 3D print templates, it's easy to make whatever shape I want. Without the pantograph, I would probably have made this part circular, and that would have worked just fine. If any of you fancy building this mechanism, you can download the drawings and CAD model from our Patreon page, and don't be afraid to modify the design to work with your equipment. Now you might think that machining from a 3D printed template would yield inaccurate results, but the beauty of the pantograph is that you can machine scaled down from your template size, which also reduces the error. This part is only 3 times smaller than the template, and it's very easy to get within a few tens of microns of the target size. To glue in the bearings, I use a light smearing of glue, applied using a cotton bud. I know this goes against my advice from earlier, where I suggested applying the adhesive in excess, but I don't want to get the excess in the bearing, and I'm okay with not achieving the full strength in this case, because the loads are small on this interface. This is a commercial screw, and frankly they leave a lot to be desired, but rather than making every single screw from scratch, sometimes it makes sense to use these, but I do like to clean up the head. For about 1 or 2 minutes of effort, it makes a huge transformation to the appearance of the screw. Now we can assemble the frame, which provides the foundation for the rest of the mechanism. Where possible, I like to assemble as I go along to check the fit of parts and make any adjustments if necessary. The damper I alluded to earlier is just a washer with a groove machined in the face for an O-ring. It doubles up as a washer for axially preloading the bearings. Now some of you might be wondering why I went into the effort of fitting ball bearings to then go and ruin those lovely low friction bearings with this damper. Now I'm pretty sure plain bearings would work just fine, but with potentially high radial loads I wanted to ensure the friction I'm introducing here is well controlled and not prone to stiction. I initially made the locking arms out of steel, and that's what you're seeing here. I thought they would benefit from the added strength over brass, but I found the friction of the arms when locating with the pins was quite high, which resulted in some stiction problems. Therefore I concluded that brass was a better material here due to the lower coefficient of friction, and it proved strong enough anyway. This might make more sense if I explained how the mechanism works. In this animation, we are actuating against the tension of the cable. At the top you can see the left push rod applying the force to index the wheel, and although the right locking arm is pushed out of the way of the rotating wheel by a cam, which is not shown here, the left arm is just pushed out of the way by a pin on the ratchet wheel, so this interface needs to slide smoothly. Going the other way, or with the tension, was harder to design for. I will leave the main cam in place here, but if I chop off the right hand side, you can see we still need a sliding interface between the pin and locking arm. Of course we have the same problem between the main cam and the locking arm pins, but in this case it's actually worse because of the geometry of the cam. I couldn't think of a good way to alleviate this friction using a geometrical approach, so I introduced these ball bearings on the locking arm pins so the pins can effectively roll over the cam instead of sliding. The watchmaker's lathe is ideal for making the various pins. For the pin you see here, I machine a groove to help locate a tension spring. The purpose of the springs is simply to pull the arms and push rods against their respective cams. I open out the holes in the locking arms with a clockmaker's broach and a standard hand reamer until the pins are a tight press fit. On the back of the locking arm, I file a chamfer to help the locking arm slide smoothly into position over the top of the wheel. This is also aided by the chamfer I machined earlier on the wheel itself. I apply a small drop of oil on the pivots as I assemble these parts. During operation, the mechanism will need to perform a complete index cycle in approximately 200 milliseconds, so it's important the pivots are free moving. Here you can see the locking arms are working perfectly. If I lift one arm out the way, the mechanism works like a traditional single direction ratchet, and if I lift the other arm out of the way, it does the same but in the other direction. The push rods and the main cam have recessors which can be machined on the pantograph using the manual Z control, and with the help of a baffle on the 3D printed template to help guide the stylus. The horn that came with the servo had a reinforcing rib running across its length, but in this case I had to remove this with a chisel. I also opened out the holes to 2mm. To attach the push rods to the servo horn, I made a custom screw, and much like the screws for the locking arms, it has a plain portion to act as a pivot and a smaller diameter thread on the end to screw into the corresponding part. The idea here is that when the screw is tightened, the push rods can still freely pivot. The screw head is slotted in the watchmaker's lathe. I've talked about the main cam attached to the servo, but we need an additional cam at the top of the mechanism to guide the push rods. This cam is positioned over the top of the push rods and servo horn by 2 spacers. When actuating, one of the push rods locates against the pin gear, but the other one doesn't need to be there until we need to actuate in the other direction. Without this stationary cam, the push rod on the right, in this case, would cause the mechanism to jam when the servo returns to its neutral position. The main cam, which is attached to the servo, was a tricky bit to figure out, because it needs a different shape depending on the direction it's rotating. I achieved this behaviour with a spring, which I made from titanium due to its inherent springiness. The principle here is that in one direction, the bearing attached to the locking arm can run over the top of the spring, but on the return the spring lifts over the top of the bearing. The way the spring interacts with the cam makes it stiff when lifting the locking arm, but floppy in the opposite direction. In practice, this worked really well, but the spring was subject to more rotational force than anticipated, so needed an extra screw to pin it in place. There was only space for this extra screw on one side due to the close clearance to the servo. I also bent the corners of the spring to help guide it over the top of the bearing. For this project, we selected a high-performance KST X10 servo due to the high torque requirements for the tendon pulling experiment. Here you can see what I mean by the tight clearance between the cam and servo. If I were to tweak the design, I might think of a more elegant way to attach the spring to the cam. So with all the parts made, let's finish the assembly and test it out. During these test runs, I've G-clamped the mechanism to the table so I can pull on the cable as hard as I can. The mechanism handled this tension no problem at all, which I am very happy about, especially considering the device is compact enough to fit in the palm of my hand. Under its normal operating speed, it's just too fast to see the mechanism working. If I index the servo slowly, here you can see how the cam spring works with the locking arm bearing. These shots are in slow motion. Here you can see some bounce on the locking arm when operating against the tension, but it still locks fine despite this bounce. Going with the tension, there is no bounce because of the way the locking arm interfaces with the pin gear. Just for fun, this is what happens if we try actuating with the tension if I disable the damper. Basically, the mechanism can't respond fast enough and skips pins. Going against the tension is fine without the damper though. We did test the mechanism on tendons in a chicken foot with Charlie and one of his undergraduate students, but it's not clear if YouTube is happy with me showing dissected chicken feet on a public video. To play it safe, I've put together a separate short video, which is available to watch for free on our Patreon page, so feel free to check that out if you're interested. Many thanks to our patrons, FortisNet and this video sponsor Brilliant for making this project happen.
Whether you're looking to learn a new skill or just want to keep your mind sharp, Brilliant helps you get smarter every day with thousands of interactive lessons in maths, science, programming, data analysis, and AI. With Brilliant's mobile app, you can learn on the go, making it easy to fit bite-sized lessons into your busy schedule. Their courses are designed for learners of all skill levels and are carefully crafted by a specialist team of teachers, researchers, and professionals to optimize your learning. All of the lessons are beautifully designed with hands-on activities and puzzles, which help to break up the lessons and reinforce new concepts as you learn. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/Cronova or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. Thanks for watching.